Hi, I'm Ben-Yaakov. This presentation is entitled Intuitive Explanation of Silicon Carbide Thermal Impedance, Safe Operating Area, and LTspice Simulation. There is a disclaimer here that the devices and simulation tools shown in this presentation are for educational purposes only. There is no endorsement or recommendation implied. The issue that I'm addressing in this presentation is the thermal problem of a transistor, and in particular the junction temperature. So here is an equivalent circuit, a thermal equivalent circuit, in which the thermal behavior is emulated by an electrical circuit. In this case, the current source represents the power which is pumped into the transistor, that is the voltage and current through it, and I'm primarily interested in this presentation in the linear mode, in that is not the switching mode, that the transistor is completely on and there is a RDS on, but rather when you have a voltage across the transistor and a current passing through it. So this will represent the power dissipated within the unit. These are the thermal resistances. This is the junction temperature is represented by the voltage here. The case temperature is the voltage here, and this is the thermal resistance between junction and case. Also, I'm showing here the thermal resistance between the case and ambient, and then we have the ambient temperature represented by, clamped by a voltage source. Now these capacitors represent thermal capacitances, and that is the amount of heat that is absorbed by the mass. You need it for transient. In DC you don't need it. That is for steady state you don't need it, because you just consider the resistance. But if you have a pulse coming in, then temperature starts rising and some of the heat is being absorbed by the mass. So these capacitors represent the thermal capacitances within the area of the die and the structure, as a matter of fact. There is a need for a distributed presentation because the heat is propagating throughout the die. You might say it's like a three-dimensional thermal transmission line, and therefore the best way is, of course, to use this ladder type of a presentation, although some cases you can get by a simpler structure. So with this equivalent circuit, you can probe into the issue of the junction temperature in the case that you have a current with just some background current, then there is a pulse, and then some more current, and a pulse, or any other profile of a current. Manufacturers are giving in the datasheet information regarding the transient behavior of the junction temperature, and one of them is the safe operating area plot, which is shown here. And let me go over it very quickly. The y-axis is current, the drain current. The x-axis is the drain to source voltage. This device is a 1200 volt device, silicon carbide, 25 milliohm, quite a hefty transistor. And then we have boundaries here. This right boundary is actually the maximum voltage that you can expose the transistor to. That's 1200 volt. And then there is a upper boundary, which is maximum current. And then this boundary here is actually the RDS on, because if the voltage is low, you cannot go above certain currents which are limited by the resistance RDS on. Okay, so in fact each point here represents the ratio between voltage and current to give you the RDS on. So this is this boundary here, and then we have these curves here, and these are for pulses. So if I have a pulse of say 100 microsecond, in order to be in the safe junction temperature, you have to be below this line, meaning that the boundary here, let's say, take for example, if the voltage of the transistor is 100 volt, then you can have a current of the pulse of the 100 microsecond of about I'd say 50 amp. Okay, so as long as you are below this line, you are okay. If you are above this line, you are supposed to violate this maximum junction temperature. Unfortunately, Cree does not give you what is the maximum junction temperature for these curves. Well, the maximum junction temperature for the transistor of Cree or Wolfspeed is 150 degrees. So you might have thought that this is 150 degrees. Well, we'll check it later on. On the other hand, some vendors like ST, of course, also give this safe operating area plot in their datasheet. And then this particular unit that they have, the silicon carbide, has specified the maximum operating temperature of 200 centigrade as opposed to 150 for Wolfspeed. I really don't understand the very big difference. In any event, regarding our discussion here, they are showing the maximum temperature for these plots. That is, they're saying, okay, these plots are for a maximum of 200 degrees. And of course, we have the same situation here. These are different pulses of different width. However, this safe operating area is good for the boundary, but does not give you information of, say, suppose you have a 100 microsecond pulse, okay, and let's say the voltage across the transistor is 100 volt. What is the junction temperature? Well, you don't get it from here. What you get here is that you can go up to a current of this value, but what about this case, this current, you just don't have this information here. You can get it from this plot, which is the thermal impedance, and what it is, it sort of takes into account the fact that if you have pulses, the temperature are not, of course, stabilized, but they are sort of a transient temperature, and this will help you to find out what is the maximum temperature due to pulses. So let's just go over it very quickly in general, and then I'll probe into it a little bit more in depth. What we have here, this is the thermal impedance, that is the thermal resistance during transient. This is the meaning of this thing. This is the pulse width, okay, so we have 1 microsecond up to 100 milliseconds. And here I'm concentrating now on one curve here, which is the single pulse. This is the curve, okay, it goes up and then it sort of clamps to this value, which is the DC thermal resistance between junction and case. So this is what is given in the datasheet as the junction to case thermal resistance. In this particular case, for this particular transistor, it's 0.24 degrees per watt, okay? But if the pulses are short, not long pulses, for example, 100 microsecond, we are at this point. And at this point, we have a certain value, okay? So this would be like 10 to the minus 3, 0.03, okay? So this will be the value here. What does it mean? It means that if the pulse is short, then the thermal resistance that you have to take into account is not this one for steady state, but rather the one for this particular case of the width of the pulse. And then we're talking here about a single pulse, okay? So this is this curve here. We'll talk about these later on. So let's have a look. What is the meaning of this single pulse line here or curve here, okay? So let's assume that we have a pulse of a power injected into the transistor, okay? This is the pulse, 100 microsecond width, and there is a certain height for the power. Now obviously the temperature will start going up. If this pulse is much longer, we are in the continuous or steady state situation, and then of course the temperature of the junction or junction to case will be the power, times the thermal resistance between junction and gate. However, if the pulse is short, temperature will rise only to this point, okay? So obviously, just power times the steady state thermal resistance is incorrect. It has to be shorter. This is exactly this line. I have just sort of marked this as the thermal resistance junction to case for pulse, okay? So this pulse is 10 microsecond, and for 10 microsecond, the value of this thermal resistance pulse is 7 millidegree per watt, as opposed to 240 millidegree centigrade per watt. So it's a much lower thermal resistance because it only got to this point. So when you multiply the power by this value from this curve, you'll get the right junction temperature. If the pulse is wider, then you'll get to a higher point, and obviously you have to look at the corresponding pulse width, which is 100 microsecond. It'll be here, and this will be 21, and this will be this point here. So this is the meaning of this plot, which is very neat for a single pulse. However, if you have a train of pulses, that is, you have some frequency with pulses of certain width, then you have to go to this area here, and let me go over it quickly here. In this case, we have the pulses coming in. Now, obviously, for this first one, we got up to here, but if this train persists, eventually we'll get to a higher temperature. And this temperature now depends on the average power as well as the duty cycle, because of course, if the duty cycle is large, then it'll go to a higher value, okay? So here are the plots now that allow you to estimate this temperature for the train of pulses. Now, the way it is specified here is this is still the width of the pulse. This is this width here. And these curves now are for the duty cycle, okay? So for any given duty cycle, you have to look for the corresponding curve here. So say if it is 10 microsecond pulse with a duty cycle of, let's say, 0.01, then this will be this value. However, if you have a current of another profile, not a single pulse, and not a train of pulses which are starting from zero, you cannot get the junction temperature from the plots that I've shown, not the safe operating area and not the thermal impedance, okay? For this, you need this equivalent circuit or this presentation, which will give you, for any profile, the junction temperature, okay? You cannot get it from here, and you cannot get it from here. This is just the limit for a single pulse, and here, this is you get a temperature for a train of pulses, not any arbitrary current profile. So you need this equivalent circuit. Some vendors will give it as a separate unit that you can sort of, during simulation, find out what is the instantaneous power, and you get this value. Or some vendors, and we see more and more vendors, are giving a model of a transistor that includes this equivalent circuit. So here is an example. This is just one example. As I've said, other manufacturers are providing similar models, and this is for Wolfspeed, the Cree. And here I am showing a transistor. This is this transistor, 25 milliohm, 1200 volt voltage. And you just put it in as a regular model of, in this case, LTspice. And the difference is that now you're getting two outputs, additional outputs. One is the case temperature and one is the junction temperature. These are coming out of here. Now, in order to examine the linear case, linear operational mode, I've set up this circuit to be a current source. And this is done by having this resistor here. Now, if I have an input pulse, say of 10 volt, and if this transistor starts to conduct, and then it will lock at the threshold voltage between gate and source, and let's say that the threshold voltage is, say, 4 volt, then the remaining 10 minus 4, 6 volt is on this resistor, being 1 ohm, you'll have a 6 amp passing through the current, while the voltage is, of course, the 1000 volt here, which is the voltage source, minus the voltage here, which is 6 volt in this particular case. You can neglect it or take it into account, okay? So this is just a tool to see how well is this model operating. So in this case, I'm feeding a pulses here of 10 volt to the gate, and the width of the pulse is 10 microseconds, and the period is 100 microseconds, meaning that we have a duty cycle of 10 to 100.1, okay? Duty cycle does not need to be entered here. I'm just taking it as a reference for comparison later on. So in this case, I've clamped this case to 25 degree, which is like representing the ambient temperature, exactly as I put it here. This is the terminal of the case. I don't have a thermal resistance between case and ambient because I'm assuming, as in most data sheets, that the case is kept constant, clamped to 25 degrees. So this resistance is 0, okay? So this goes directly to this clamping temperature. Of course, if I would have had a heatsink and I would have known the thermal resistance of the heatsink, I could have put here a resistor, okay? But in this case, I'm just examining parameters against the data sheet, and most of the parameters in the data sheets are given for a case temperature of 25 degrees or some other. And here is what I am getting. And you can see, we see first of all the junction temperature. This is the output of the junction. Obviously, I'm starting from a low temperature, 25. Doesn't show exactly, but this is 25. And then we go up, and here I'm already at a steady state. Here I'm showing the drain current. It's about 6, a little bit actually lower than that. We'll see it in a minute. And then I have here the gate to source voltage, which threshold voltage. And here I have it in an expanded scale in this region here. I see that the temperature went up to about, 170. We'll see it later on. And then the currents are about 6 amp. And this is the gate to source voltage. We see here some peak here due to probably capacitances, and then we have this value here. We'll see it later on, the exact value. Okay, so this is a typical run. I don't have to add any information. All the thermal information is within the model of the transistor. Okay, so here are some other plots with some more information for same run. Again, junction temperature, here it is. Now I've measured it to be 175 degrees centigrade. Here I'm showing the power. The power is measured by looking at the current here, because this current here is this current, which is coming from the current source, which represent the power. And at steady state, of course, the current through the capacitor is 0. So we see here actually the power coming from here to the output. Okay, so that's the current through voltage source V4. And here it is. This is at this point here, this region here, it's 550. Now the current now, I've measured it to be 5.5 amp, the current here. This is the current that passes through I4. This is this current here. So this is 5.5. Now we can do a sort of a sanity check here. The voltage is 1000 volt. The current is 5.5. The duty cycle is 0.1. So the average power is 550 watts. This is what I see here, 550 watts. So everything seems to be okay in terms of the inner parameters of this model. Now I can check it against this thermal impedance. Okay? Check it here. So I found that from the simulation that the temperature should have gone up. Here it is, 175. So we can get this number for this particular case, which is a simple case because this is a train of pulses, which is compatible with this plot. Now we have a 0.1, well, I sort of covered it, but this is a duty cycle of 0.1. We have 10 microseconds. So the thermal resistance or thermal impedance is 0.03, okay, or 30 milli-degrees centigrade per watt. Now the power we already know is 5.51 kilowatt. This is the peak power which you are using here. You are not using here the average, you are using here the peak. So we have the peak power of 5.5 kilowatt, and we multiply this 5.5 kilowatt by 30 this milli-degrees centigrade per watt, 0.03, and I'm getting 165. Now you have to add to it 25 degrees because this is just the junction to case, so I have to add the 25 degree. I'm getting 190. In the simulation I got 175. Well, that's not that bad. Well, could have been better, but it's pretty good. Let's have a look now at this safe operating area plot and see where we are at as compared to the model. Okay, so I have a case here, which I marked here, of 1000 volt, and I see that I'm getting to the limit here with a current of 18 amp. Okay, this is 10, this will be 20, so it's about 18 amp. Okay, so I now can simulate this case with the model, and in this case, here is the pulse. Okay, the single pulse. Start from 25 degrees going up to 106. This is a 10 microsecond pulse. This is the case that I'm looking at. And this is 106, while the maximum junction temperature specified by the manufacturer is 150. It's a long way. It's a very long way, okay? So I don't understand why the limit here is 106 only. So just to see if maybe this is a wrong point or whatever, I've tried another point. In this case it's 100 volt, okay? So I've adjusted the voltage so to be 100 volt and the current to be 50 amp with a pulse width of 100 microsecond. And here is what I'm getting in this case. This is the temperature of the pulse. This is the current, 50 amp. And you see that I'm getting again 109. So obviously the limit here is probably 100 volt. This is a little bit too low, okay? So it sort of underestimates a big safety factor. And for a 150 degree device, setting the limit here to 100, it's a little bit too much. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.